Two trains, gleaming engines of steel and steam, race along twin lines of polished track, slicing through the fog of dawn. They are perfect parallels, destined to run side by side forever, never touching. The crowd cheers as they thunder past, a spectacle of symmetry and speed. But then, impossibly, a scream cuts the air. The tracks converge. The trains collide. It's a scene that defies every rule of reason. After all, parallel lines, by definition, never meet. And yet, in that brief moment of catastrophe, something deeper is revealed. An unsettling hint that perhaps the geometry of the world we take for granted is not what it seems. For centuries, humanity has clung to the comforting logic of Euclid, the Greek polymath whose work built the very foundation of geometry. His 5 postulates became the scaffolding upon which we constructed reality itself. Lines, angles, planes, certainty. But one postulate, the 5th, always resisted proof. The parallel postulate claimed that through any point not on a given line, there is exactly one line parallel to it. It was a simple enough idea, but it refused to yield under the weight of logic. For almost 2,000 years, the brightest minds in mathematics tried and failed to prove it. Then, in the 19th century, a few brave thinkers asked a heretical question. What if it wasn't true? That moment cracked open a new universe. From the depths of their equations emerged worlds where the rules of straight lines and perfect parallels no longer held, where two parallel paths could bend through space and meet again at infinity. These strange geometries, non-Euclidean as they came to be known, would go on to transform not just mathematics but physics, philosophy, and even our understanding of the cosmos itself. Because if space can curve, then reality can too. Our story begins in that mathematical rebellion, but it doesn't end there. It stretches across centuries, from medieval cathedrals to modern telescopes, from the obsessions of monks and bishops to the equations of Einstein and beyond. It's a story of light and shadow, of expansion and infinity, of questions so large they reshape the meaning of space itself. Today, the echoes of that rebellion ripple through every galaxy we see. The universe, we are told, is expanding, an ocean of stars stretching outward from a moment of unimaginable density and heat. But as we gaze into that vastness, one question remains, ancient and relentless. If the universe is expanding, what is it expanding into? It sounds simple enough, but it's a question that rattles the core of physics. It asks us to confront whether space itself has an edge, or whether we are trapped inside a loop of endless geometry. Is our cosmos infinite, or folded back upon itself like a cosmic origami? Are we racing on invisible rails that will never meet, or are we the trains destined to collide, proving that even parallels can touch? To answer that, we'll need to venture into realms where light curves back on itself, where energy slips away into hidden dimensions, and where the universe might be nothing more than a hologram projected from a higher reality. This is not just a story of astronomy or mathematics. It's a story of perception, of how the human mind, in its relentless search for order, keeps finding that the universe refuses to sit still. And it all begins with a warning, whispered across centuries. You must not attempt this approach to parallels. I have traversed this bottomless night, which extinguished all light and joy in my life. Heed the warning or not, the path lies ahead. The night of geometry awaits. Part 1. The birth of the impossible geometry. The year is around 300 BCE. In the bustling city of Alexandria, at the edge of the known world, a scholar sits beneath the flickering light of an oil lamp. Sheets of papyrus scatter across the wooden desk before him, filled with straight lines and perfect circles drawn by a trembling hand. His name is Euclid, teacher, philosopher, and perhaps the most influential geometer who ever lived. His book, The Elements, will outlast empires. For over 2,000 years, it will define not just mathematics, but the very structure of thought itself. Every student who has ever held a ruler and compass, every engineer who has ever drafted a bridge, every physicist who has ever drawn a diagram of the universe, they all trace their lineage back to Euclid. In The Elements, Euclid laid out 5 simple truths, axioms. He called them statements so obvious they needed no proof. that through any 2 points a straight line can be drawn, that a line can be extended infinitely in either direction, that all right angles are equal, that a circle can be drawn from any point with any radius. And then there was the fifth one, the troublesome one, the one about parallels. It stated, in essence, that if you draw a line and a point outside it, there is exactly one line that can pass through that point and never meet the original, no matter how far both are extended. For generations, mathematicians accepted this reluctantly. It worked, yes, but it felt wrong. Why should something so fundamental sound so much more complicated than the others? Why did the geometry of the universe need this strange, fragile assumption to hold it together? The problem was too elegant to ignore, and so, century after century, scholars tried to prove the fifth postulate using only the first four. But every attempt ended in frustration or madness. The Persian polymath Omar Khayyam wrestled with it in the 11th century. The Italian priest Girolamo Sacchari tried again in the 18th, convinced he could tame Euclid's wayward axiom. Sacchari built an entire system of imaginary triangles, assuming the fifth postulate was false, hoping to find a contradiction that would restore Euclid's rule. But the contradiction never came. Instead, something strange happened. The geometry still worked. Lines that should never meet did. Triangles added up to more or less than 180 degrees. And yet it was consistent, logical, complete. Sacchari, horrified by what he had discovered, destroyed much of his work before his death. Others who followed him would face the same crisis. A geometry where parallel lines met not in defiance of logic, but because logic demanded it. It would take until the 19th century for anyone to accept the unthinkable, that there was more than one geometry. In a small Hungarian town, a young mathematician named János Bolyai wrote a letter to his father, also a mathematician. "I have created a new, strange universe from nothing," he confessed. "Out of nothing I have created another world." Independently, across Europe, a Russian genius named Nikolai Lobachevsky was reaching the same conclusion. The geometry that Euclid had built was not wrong, but it was not unique. There existed other worlds of pure reason, where space itself could bend, curve, and fold. It was the birth of non-Euclidean geometry, an impossible geometry that suddenly wasn't impossible at all. For the first time, humanity was forced to confront an idea more radical than any before, that space itself might not be flat. This revelation would ripple outward through every discipline. Philosophers began to wonder if truth itself could bend. Theologians debated what it meant for divine perfection if even geometry, once thought to be the handwriting of God, could take multiple forms. And centuries later, Albert Einstein would take this strange, curved geometry and use it to describe the universe itself. Space, time, and gravity, all intertwined in a vast, invisible fabric that could warp and stretch under the weight of stars. But before Einstein, before relativity, before telescopes and cosmic expansion, there was another man who glimpsed this strange connection between light and geometry long before the modern age. A man whose vision of creation predated the Big Bang by 700 years. His name was Robert Grosseteste, bishop, philosopher, and scientist of the 13th century. And while his peers saw light as divine metaphor, Grosseteste saw it as the first architect of the universe itself. He believed that everything, every atom, every star, had once been light, expanding outward from a single point before condensing into matter. In an age when Earth was thought to be the unmoving center of all things, Grosseteste had already imagined a cosmos in motion. He didn't have the mathematics to prove it. He didn't have telescopes or data or equations. But he had an idea, one so bold that it would take the world nearly a millennium to catch up. And in that idea lay the seed of everything that would follow. The expansion of the universe, the bending of space, the death of certainty, and the rise of a new cosmic question that still haunts science today. Because if Grosseteste's vision was right, if light truly did create everything, then perhaps it never stopped expanding. And if that's true, then we are still inside that first flash of creation, still riding its wave of light, still trying to understand what, if anything, lies beyond it. Part 2, the Big Bang Bishop. It's the 13th century, and Europe is a continent of cathedrals and contradictions. Faith rules the hearts of men, yet curiosity gnaws at the edges of dogma. The air smells of incense and parchment, and in candlelit cloisters, a quiet revolution is beginning. Not with swords or banners, but with questions. In the English city of Lincoln, a bishop named Robert Grosseteste sits hunched over a manuscript. His robes mark him as a man of God, but the glint in his eyes betrays a different kind of devotion, one to light, logic, and the hidden order of the cosmos. Grosseteste was no ordinary clergyman. To most of his contemporaries, the world was an eternal, unmoving sphere crafted whole by divine will. The heavens turned above, but the universe itself did not change. Grosseteste disagreed. He saw motion in everything, light in constant expansion, matter coalescing from brilliance into substance. He called it lux, the primal light. In his treatise De Luce, he wrote of creation as a flash radiating outward from a single infinitesimal point, spreading through nothingness, dragging matter into existence as it went. The universe, he said, began with illumination. Centuries later, astronomers would describe this same event with a different name, the Big Bang. For Grosseteste, this wasn't mere mysticism. He approached light not as metaphor, but as a physical principle, something that obeyed rules that could be studied and reasoned about. He experimented with lenses, prisms, and mirrors. He tried to understand rainbows, not as divine symbols, but as the bending of light through droplets of water. This was a radical idea for his time. The Church often saw questioning creation as bordering on heresy. Yet Grosseteste persisted. He believed that to study the natural world was not to deny God, but to glimpse his method. Truth, he wrote, cannot contradict truth. Still, not everyone shared his conviction. His insistence on reform and his relentless curiosity drew the ire of both King Henry III and Pope Innocent IV. Grosseteste died in 1253, and rumors spread that his restless spirit returned to haunt the Pope in vengeance, a spectral punishment for those who stifled knowledge. And yet, centuries after his death, his ghost would live on in another way. The light he spoke of, the expanding universe of radiant matter, would find new life in the mind of another priest. 700 years later, in 1927, a Belgian cleric named Georges Lemaitre would take up Grosseteste's torch. Lemaitre was an unlikely cosmologist. Before he was a priest, he was a soldier, an artillery officer who narrowly escaped death when a cloud of chlorine gas drifted away from his trench during the First World War. After the war, he turned to the heavens. He studied physics under Arthur Eddington at Cambridge, then mathematics at MIT. He was fascinated by Einstein's new general theory of relativity, the strange idea that space and time could bend and stretch like a living fabric. In that bending, Lemaitre saw something extraordinary. He realized that if the equations of relativity were taken seriously, the universe could not remain static. Space itself would have to expand or contract. The cosmos was not a still cathedral, it was breathing. When he published his paper proposing an expanding universe, Einstein himself scoffed. "Your calculations are correct," Einstein told him, "but your physics is abominable." But Lemaitre persisted. He called his vision the hypothesis of the primeval atom, a universe that began as a single dense point, expanding outward into everything that exists. It was, in every sense, the scientific heir to Grosseteste's lux. Then, in 1929, a quiet man at Mount Wilson Observatory provided the proof Lemaitre needed. Edwin Hubble had been measuring the light from distant galaxies and found something astonishing. The further away a galaxy was, the faster it appeared to be moving away. The universe, it seemed, was stretching in all directions. Suddenly, Lemaitre's primeval atom didn't sound so heretical after all. The universe was expanding. And yet, even this revelation raised new mysteries. If everything is moving apart, where did it begin? What lies outside the boundary of all this motion? Is there an edge? A center? To explain this, Lemaitre reached for a metaphor, a simple one. Imagine, he said, a loaf of raisin bread rising in the oven. The dough expands, and as it does, every raisin moves away from every other. No raisin is special. None sits at the center. The dough itself stretches everywhere, evenly. That dough is space. As it expands, it doesn't move into something else, it creates more of itself. The galaxies are carried along, not like ships through an ocean, but like crumbs baked into the bread. It's an idea so simple it feels impossible. We live inside an expanding loaf with no edges and no outside. Space is not expanding into anything. It is the expansion. And yet, Lemaitre's revelation opened as many questions as it answered. If space is stretching, does energy stretch with it? If the universe grows, does it conserve the same total energy, or does something vanish in the process? The further astronomers looked, the stranger it became. Distant galaxies glowed redder than expected, their light stretched by the very expansion of space through which it traveled. The cosmos, in expanding, was also cooling. The light of creation was dimming, stretched thin across eternity. The further back scientists traced the expansion, the hotter and denser the universe became. Until, finally, all paths led to a single moment, when all of space, time, matter, and energy were compressed into a single infinitesimal point. Lemaitre's primeval atom, grossest lux, the first instant of everything. But if the universe has been expanding for 13.8 billion years, then the question remains, the same one that haunted both priests and physicists alike. If the cosmos began as a point and has been expanding ever since, where is it expanding into? Is there a boundary beyond which nothing exists? Or are we trapped inside a loop of light and geometry, forever mistaking the shape of our own prison for infinity? To answer that, we'll have to look beyond galaxies, beyond gravity, and even beyond the universe itself, to the very geometry of reality. Because before we can understand what the universe expands into, we must first understand what it is made of. Part 3. The shape of the cosmos high above the cratered plains of the moon. A spacecraft glides in silence. Below, sunlight carves sharp shadows across a landscape frozen in time. Mountains that have never felt rain. Plains that have never known wind. From this desolate perch, you can see the scars of human history mapped in craters named for the minds that shaped our understanding of the universe. Einstein, Hubble, Slipher, Lemaitre. And then 2 more craters on opposite sides of the lunar surface, separated by thousands of kilometers yet connected by a deeper symmetry. Minkowski and de Sitter. It's almost poetic that they lie apart. The men they're named after held opposing visions of how the universe is shaped, and in their disagreement lies the key to understanding what the universe is expanding into. Hermann Minkowski was a mathematician, a man of cold logic and beautiful equations. He was once Albert Einstein's professor, though he found his student unimpressive. He is a lazy dog who never bothers about mathematics, Minkowski reportedly said. And yet, years later, Einstein's own theory of relativity would depend entirely on Minkowski's mathematics. Minkowski introduced a radical concept, that space and time are not separate things but one unified entity, spacetime. It's not just a poetic phrase, it's a geometric reality. Everything that happens in the universe, the birth of stars, the path of planets, the ticking of your watch, occurs within this four-dimensional fabric. In Minkowski's version, the universe is flat. That word, to most of us, suggests 2 dimensions, a sheet of paper, a calm sea. But in cosmology, flat doesn't mean shallow. It means that the geometry of the universe follows the familiar rules of Euclid. Parallel lines never meet. Triangles always add up to 180 degrees. It's the geometry we grew up with, predictable, intuitive, safe. But Willem de Sitter, a Dutch astronomer and mathematician, envisioned something different. His universe wasn't flat, it was curved. And the kind of curvature it had would determine everything about its fate. In a closed universe, like the surface of a sphere, travel far enough in one direction, and you'll return to where you started. Straight lines, or geodesics, bend gently through space until they reunite. Parallel lines that should never meet eventually do. In an open universe, the opposite happens. Space curves away from itself, like the surface of a saddle or a Pringles chip. Here, triangles add up to less than 180 degrees. Light, traveling across billions of light years, diverges ever outward, never looping back. And then, of course, there is flat space, Minkowski space, where the angles behave exactly as Euclid said they should. 3 possibilities. 1 reality. So which one do we live in? To find out, astronomers turn to the oldest light in existence, the cosmic microwave background, or CMB. It's the afterglow of the Big Bang, a faint radiation still echoing across the universe 13.8 billion years after its birth. The CMB is a map of the infant cosmos, imprinted with tiny ripples of temperature, some regions slightly hotter or denser than others. Those ripples were the seeds of everything, the galaxies, the stars, the voids between them. By studying their size and pattern, scientists could reverse engineer the geometry of the universe itself. When they did, the answer shocked them. The measurements showed that those ripples lined up almost perfectly with the predictions of a flat universe. Not spherical, not saddle-shaped, flat. But flat doesn't necessarily mean infinite. Imagine taking a sheet of paper and curling it into a cylinder. From the perspective of an ant crawling along its surface, the world still feels flat. Walk in one direction long enough and you'll loop back to where you began. You could even connect both ends of the cylinder, forming a torus, a cosmic donut. Still flat, yet finite. Still endless in appearance, yet closed in structure. Could our universe be like that? A vast 3D torus looping in on itself? If it is, then light could travel in circles, allowing us to see the same galaxy repeated in multiple directions across the sky, a kind of cosmic hall of mirrors. Astronomers have searched for these repeating patterns in the CMB, looking for matching fingerprints of structure on opposite sides of the heavens. So far, none have been found. But there's a twist. Some topologies, like the bizarre Hansch-Went manifold, a more complex version of the torus, could hide those repetitions entirely, folding space in ways that prevent us from seeing the reflections at all. So the question remains maddeningly open. Is the universe infinite, stretching forever in all directions? Or is it finite, but unbounded? A self-contained loop where out there eventually circles back to here? Either way, the implications are profound. If the universe is infinite, it cannot be expanding into anything. Infinity cannot grow larger. It can only stretch within itself. But if the universe is finite, a vast, folded shape in higher dimensions, then perhaps it is expanding into something beyond our comprehension. And that brings us back to the same haunting paradox that has lingered since Grostist's first vision of creation. If everything is expanding, where does it go? It's a question that no telescope can answer directly. Not yet, but there are clues hidden in the fabric of space itself, clues that suggest the cosmos we inhabit may not be what it seems. To understand them, we'll need to step deeper into geometry, into the strange, beautiful mathematics that lets space twist and stretch without ever leaving itself. Because before we can comprehend what lies beyond the universe, we have to understand how space can bend within it. Part 4, The Curvature of Reality. It begins, as so many great revelations do, with a schoolboy and a sum. Late 18th century Germany. The air in the classroom is heavy with chalk dust and boredom. A teacher scrawls a tedious exercise on the board. Add up all the numbers from 1 to 100. The students groan and begin scratching on their slates. All except one small boy at the back of the room. He stares for a moment, then writes a single number and sets down his pencil. 50-50, he says. The teacher blinks. How did you? The boy, Carl Friedrich Gauss, had seen what others had not. That the numbers could be paired 1 plus 100, 2 plus 99, 3 plus 98, and every pair added to 101. 50 such pairs made 50-50. That flash of insight, seeing the hidden pattern behind the obvious, would become Gauss's gift to the world. And it would one day reshape how we understand the universe itself. Decades later, Gauss would turn his mind from arithmetic to geometry. At the time, the intellectual shockwaves of Bolyai and Lobachevsky's impossible geometries were spreading across Europe. The idea that space itself might bend was scandalous and intoxicating. Gauss wondered, could such curvature be measured, not in imagination, but in reality? He took to the mountains near Göttingen with surveyors, measuring the angles of enormous triangles stretched across the landscape. If the sum of those angles differed from 180 degrees, space itself must be curved. The results were tantalizingly close, so close that the error might have been in the instruments, not in nature. But the seed was planted. In 1827, Gauss published a paper whose Latin title sounded almost modest, Theorema Egregium, the remarkable theorem. Its consequences were anything but modest. Gauss had discovered that the curvature of a surface could be known entirely from measurements made on that surface, without needing to step outside it and look back. This was revolutionary. Until then, mathematicians imagined curvature as something that required a higher dimensional perspective. A sheet bending into a third dimension, for example. Gauss proved otherwise. Curvature could be an intrinsic property, knowable from within. A flat sheet of paper has zero intrinsic curvature. Roll it into a cylinder, and though it looks curved from the outside, an ant crawling along its surface would find that the geometry hasn't changed. Triangles still sum to 180 degrees. The cylinder is flat in Gauss's sense. But a sphere, like Earth or the Moon, is different. The ant doesn't need to climb into the air to realize something is strange. Draw a triangle from the North Pole to the equator, turn 90 degrees, follow the equator, turn again and return north. The angles add to more than 180. The surface itself reveals its curvature. This insight, distinguishing between extrinsic and intrinsic curvature, would echo far beyond mathematics. It would become the language through which physicists describe gravity, motion, even time. 30 years later, another mind would push Gauss's ideas further. Bernhard Riemann was once Gauss's student. Quiet, painfully shy, yet possessed of a mind as deep as the space he sought to describe. In 1854, he delivered a lecture that began cautiously and ended by tearing open the boundaries of geometry. Riemann asked, what if Gauss's methods could be extended beyond the surfaces of our world? What if curvature could exist not just in 2 or 3 dimensions, but in any number we could imagine? He introduced the concept of manifolds, mathematical spaces that could be curved in ways no human eye could visualize. In these spaces, the shortest path between 2 points, the geodesic, might appear curved when projected into lower dimensions, but was straight within its own. Riemann's geometry was a geometry of the unseen. And though he could not have known it, his equations would become the scaffolding for the greatest scientific leap of the 20th century. 60 years later, a patent clerk in Bern would take those ideas and do something extraordinary with them. Albert Einstein's general theory of relativity proposed that gravity is not a force pulling masses together, but the curvature of four-dimensional spacetime itself. Matter tells spacetime how to curve. Spacetime tells matter how to move. In this picture, Earth doesn't orbit the Sun because an invisible force tugs at it. It follows a straight line, a geodesic, through curved spacetime. What looks like a curve in 3 dimensions is straight in 4. To visualize this, think again of those transatlantic flights arcing across a flat map. From above the globe, each is perfectly straight. It only looks curved because our map flattens a sphere into a rectangle. Likewise, in the higher dimensional geometry of spacetime, planets follow straight paths that only seem to bend when seen through our limited, 3-dimensional eyes. Einstein's equations also explained a host of mysteries that Newtonian gravity could not. Light itself bends when it passes near massive objects, a phenomenon confirmed during a solar eclipse in 1919, when starlight curved around the Sun exactly as Einstein predicted. Later, astronomers would find entire galaxies whose gravity warped the light behind them, creating cosmic mirages, rings, arcs, and ghostly duplicates of distant galaxies. These gravitational lenses became one of the universe's own experiments, proving that space really does curve. With Einstein, Gauss's abstract theorem became the architecture of reality. Intrinsic curvature was no longer a mathematical curiosity. It was the texture of the cosmos. And that brought with it a remarkable implication. If curvature can be described entirely from within, There's no need for an external space into which the universe must bend or expand. The geometry of spacetime is self-contained. In other words, the universe doesn't need to expand into anything. Its expansion is a change in the metric itself, a stretching of distances defined by its own internal geometry. Yet, just as Grosseteste and Lemaitre discovered, explanation never means finality. For even as relativity seemed to close one door, another creaked open behind it, a question Einstein himself could never silence. If the universe's curvature defines its gravity, could there be other kinds of curvature, hidden ones, folded dimensions beyond the four we know, that leak gravity away, or give birth to universes parallel to our own? The next step in the story leads there, into dimensions we cannot see, and into theories where spacetime itself may be only a surface, a brain, floating in a higher dimensional sea. Part 5. The Hidden Dimensions. It is February 2021. In a quiet underground lab, two tiny gold spheres, each barely larger than a grain of rice, hang suspended by impossibly thin threads. Around them, the air is still, every vibration dampened, every source of interference eliminated. The scientists are waiting to watch gravity, nature's most familiar force, do something no one has ever seen before, bend ever so slightly differently. For centuries, we've known how gravity behaves. Double the distance between two objects, and their gravitational pull weakens to a quarter. Triple the distance, and it drops to a ninth. This pattern, called the inverse square law, is so deeply woven into our understanding of the universe that we use it to navigate spacecraft and predict the orbits of planets. But this experiment was looking for something stranger, a hint that gravity at tiny scales might deviate from the rule. Because if it did, it could mean something extraordinary. That gravity isn't confined to our universe at all. It might be leaking away, escaping into dimensions we can't see. For physicists, this possibility is not fantasy. It's a direct consequence of one of the boldest ideas in modern science, the brane-world hypothesis. The name comes from membrane, or brain, as physicists shorten it, a surface that can exist in higher dimensional space. Imagine a soap film floating in the air. The film is two-dimensional, but it exists within a three-dimensional world. Now imagine that our entire universe is such a film, a four-dimensional brain embedded in a higher dimensional hyperspace known as the bulk. Within this framework, everything we experience, space, time, matter, light, exists only on this brain. We are trapped on its surface, unable to perceive or move through the extra dimensions around us. Except, perhaps, for one thing, gravity. To understand why, we must turn to string theory, the long-sought bridge between Einstein's smooth, continuous universe and the jittering quantum chaos of the subatomic world. In string theory, every fundamental particle is not a point, but a vibrating string. The frequency of the vibration determines the particle's nature. One pattern of vibration becomes an electron, another a photon, another a quark. The universe, in this view, is less like a machine and more like a symphony. But these strings can be of two kinds. Open strings have ends. Closed strings form loops. Open strings are tethered to the brain. They can only vibrate and move within the universe we know. The forces they carry, like electromagnetism and the strong and weak nuclear forces, never escape the brain's surface. Closed strings, however, are self-contained. They have no ends, and therefore nothing to tether them. They can wander freely through the bulk. Physicists believe that gravity's messenger particle, the hypothetical graviton, is made of such a closed string. If true, this would explain one of the oldest puzzles in physics, why gravity is so much weaker than the other fundamental forces. Every time we drop a ball or feel the pull of Earth beneath our feet, the gravitational field we experience is only a fraction of the true strength. Most of it has leaked away into higher dimensions. It's a mind-bending notion, but it's not without evidence. In the late 1990s, two physicists, Lisa Randall and Raman Sundram, developed a set of models showing that a universe with extra dimensions could naturally produce the weakness of gravity we observe. These extra dimensions wouldn't have to be large. They could be curled up so tightly that we simply can't detect them. Imagine a garden hose viewed from far away. It looks like a one-dimensional line. But up close, you see that it's actually a tube. Objects could, in theory, move around its circular cross-section. Likewise, extra dimensions could exist all around us, compactified into microscopic loops beyond the reach of our senses. If this is true, then the universe is not expanding into nothing. It is expanding within a higher dimensional bulk, its surface stretching across unseen dimensions like an inflating bubble. But theories alone are not enough. The physicists in that 2021 laboratory were testing precisely this idea. If gravity leaks into higher dimensions, then the inverse square law must break down at some tiny scale. Instead of weakening with the square of the distance, it would weaken faster, perhaps with the cube. The problem is, gravity is absurdly weak. The gravitational attraction between those two gold spheres is so faint that even the faintest vibration of a passing truck, or a whisper of air, could drown it out. The experiment took months to perfect. The results, when they finally came, were disappointing to some, but crucial nonetheless. Within the limit of their instruments, gravity still followed the inverse square law down to 40 millimeters. No sign yet of leakage. Still, physicists remain undeterred. Their models suggest that deviations might appear at distances smaller than a millimeter, lengths where even the tiniest dust grain could overwhelm the signal. For now, the extra dimensions, if they exist, remain hidden. But the brain-world concept offers another tantalizing possibility. What if the bulk doesn't just allow gravity to leak out of our universe, but also allows new universes to be born within it? Each brain could be a universe of its own, floating like a soap bubble among countless others. Some theories even suggest these brains could collide, cosmic cataclysms where entire universes crash together, triggering big bangs of their own. If so, then the origin of our universe might not have been a single moment of creation, but an impact, a collision between brains in the higher dimensional bulk. A flash of unimaginable energy that became the cosmos we inhabit. The echoes of that collision could still reverberate through spacetime today, visible as subtle patterns in the cosmic microwave background, or as ripples of gravitational waves washing through the universe. If we ever detect them, if we can prove that our universe once collided with another, it would change everything we think we know about existence. Because then, the answer to the question, what is the universe expanding into, would be clear: into others. But before we can chase those collisions, before we can map the invisible dimensions that might cradle our universe, we must return to something older and stranger. Because even if the cosmos stretches into a higher dimensional bulk, there remains one even deeper mystery: why the laws of physics seem to mirror each other across these boundaries. Somewhere, hidden in the mathematics of string theory and curved space, lies a principle that may unite both the bulk and the brain, the infinite and the finite. A principle that suggests our entire universe, everything we see, feel, and are, might be nothing more than an illusion projected from a deeper reality. A hologram. Part 6. The holographic universe. Imagine standing before a credit card hologram. Tilt it one way, and the image of a globe shimmers into view. Tilt it another, and it vanishes. The hologram looks three-dimensional, but it isn't. Every detail of that illusion, every line, every glint of depth, is encoded on a flat, two-dimensional surface. Now imagine that the universe itself works the same way. That our three-dimensional reality, with all its stars, planets, and people, is not the fundamental structure of existence but a projection. A cosmic hologram cast from a deeper, higher dimensional truth. Sounds like science fiction. Yet this is one of the most daring and influential ideas in modern theoretical physics. The holographic principle. The idea didn't come from nowhere. It was born from paradox, specifically the paradox of black holes. In the 1970s, physicist Jacob Bekenstein proposed that the amount of information contained within a black hole, the total entropy, or measure of disorder, wasn't proportional to its volume as one might expect, but to its surface area. The more surface area the black hole had, the more information it could store. Stephen Hawking's later discovery that black holes radiate energy confirmed it. The entropy of a black hole scales with the square of its radius, not its cube. Information, it seemed, was written on the event horizon, the two-dimensional boundary, not inside it. It was as if reality itself were whispering a secret, that the universe might encode its deepest truths on surfaces, not volumes. Decades later, this notion would collide with another great breakthrough: string theory. As physicists explored string theory's many mathematical landscapes, they discovered a startling relationship between two seemingly different kinds of worlds. One was a five-dimensional universe shaped by anti-de Sitter space, a warped cosmos with negative curvature, like a cosmic saddle. The other was a four-dimensional field theory, a system governed by the rules of quantum physics. In 1997, an Argentine physicist named Juan Meldacena connected the two. He proposed what would become one of the most celebrated insights in modern physics: the ADS/CFT correspondence. ADS stands for anti-de Sitter space, that five-dimensional bulk. CFT stands for conformal field theory, a four-dimensional quantum field theory defined on the boundary of that bulk. Meldacena's discovery suggested something staggering. Every event inside the higher dimensional bulk could be perfectly described by information encoded on its lower dimensional boundary. Gravity, matter, and even the geometry of space inside the bulk correspond exactly to the quantum interactions on the surface. The two descriptions, gravity in 5 dimensions and quantum physics in 4, are not merely similar. They are identical. In essence, the universe inside the bulk is a hologram of its boundary. If the ADS/CFT correspondence is true, then reality itself can be understood as a kind of duality, two descriptions of the same thing. What we perceive as gravity and curvature in the higher dimensional realm could emerge entirely from quantum processes on a lower dimensional surface. But there's a catch. Our universe does not appear to be anti-de Sitter space. The cosmos we observe is flat or slightly de Sitter, meaning it has positive curvature, consistent with an expanding universe driven by dark energy. Meldacena's correspondence works beautifully in mathematical universes with negative curvature, but less so in the one we inhabit. For decades, physicists have been trying to extend the holographic principle to de Sitter space, to model a universe more like our own. The equations become treacherous, the correspondences blur. Yet the dream persists. Because if the principle holds, if even our universe can be described this way, it changes everything. To understand what that means, consider what information actually is. Every atom, every photon, every quantum field carries bits of information. What it is, where it is, how it interacts. The holographic principle says that the total amount of information needed to describe everything inside a region of space, every planet, every galaxy, every heartbeat, can be fully represented on its surface. In other words, the universe may not contain its own data. It may be its data. We are patterns etched into the cosmic boundary, living inside the illusion our information creates. And the implications go even deeper. If reality is holographic, then the question of what the universe is expanding into might be meaningless, not because there's nothing beyond it, but because the beyond is already encoded within. The bulk and its boundary, the inside and outside, are just two sides of the same informational coin. From the perspective of the holographic universe, expansion is not motion into new space. It's the unfolding of information, the revelation of what was always there. Yet, for all its elegance, the holographic principle is maddeningly hard to test. No experiment yet can distinguish between a universe that's fundamentally holographic and one that isn't. Physicists have found hints, peculiar correlations in quantum entanglement, gravitational wave data that might reveal holographic noise, but nothing definitive. Still, the theory's beauty lies in how it unifies the deepest conflicts in physics. It bridges the smooth continuum of Einstein's spacetime with the granular probabilities of quantum mechanics. It makes gravity and quantum theory, long considered incompatible, speak the same mathematical language. To many scientists, that elegance is too profound to be coincidence. If the holographic principle is true, then the universe is not a place but a process, an infinite feedback loop where information on the boundary manifests as physical reality within. We are not observers standing outside creation. We are the projections of its code. And perhaps that code does not merely exist. Perhaps it expands. Not into empty space, but into new states of information, Each galaxy, each moment of time, a fresh layer of the cosmic hologram being written. To understand what that means for us, for matter, energy, and the ultimate fate of the cosmos, we must look again at the question that started it all. If the universe began with light expanding from a single point, then what happens when that light runs out? Does expansion ever end, or does it carry us toward a limit that isn't a boundary, but a mirror? Part 7. The edge that isn't there. We often imagine the universe as something like a balloon, an object growing larger and larger in space, its surface stretching outward into some vast emptiness. It's a comforting picture. Simple, visual, human. But it's also wrong. The universe doesn't have an edge. Not in any physical sense. There's no cosmic wall, no border where galaxies run out and nothing begins. No frontier where you could step outside and look back at creation from the outside. In fact, the idea of an edge is a misunderstanding born of the limits of our intuition. When we speak of expansion, we think of an object growing inside something else, a balloon inflating within a room, or ripples spreading through water. But the universe isn't expanding into anything. It's the very fabric of space itself that's stretching. To see why that's so difficult to grasp, let's go back to that balloon analogy, but with one crucial adjustment. Imagine the balloon again, but now picture yourself not outside it, but on its surface. The two-dimensional creatures living on that surface, call them flatlanders, can move in any direction across it, yet they cannot perceive the third dimension into which the balloon expands. For them, the surface is everything. As the balloon inflates, every point on it moves away from every other point, but no new surface is added. The flatlanders see their world growing, yet from their perspective, there's no outside to grow into. Space itself is stretching. The distances between them increase, but there's no edge. Our universe behaves the same way, except we are not two-dimensional beings on a balloon surface, but three-dimensional ones inside a four-dimensional spacetime. We can observe the stretching, but we can't step outside to see what it's stretching into. Because there is no into. The expansion is intrinsic, not extrinsic. This is where the power of geometry becomes more than mathematics. It becomes revelation. In the 19th century, Gauss and Riemann taught us that curvature and expansion can exist entirely within a space, without reference to any higher dimension. The universe doesn't need an embedding space, a larger container, to curve or stretch. It curves and stretches within itself, defined by its own geometry. That's why asking what lies beyond the edge of the universe is a bit like asking what's north of the North Pole. The question assumes a framework that doesn't exist. But still, the question persists not because it's foolish, but because it touches something deeper than geometry. It speaks to our intuition that every boundary must conceal something beyond it, that every horizon implies another world on the other side. And in a strange way, modern physics agrees. If the universe truly has no edge, then the most distant regions we can see, the faint glow of the cosmic microwave background, are not the outer limits of existence, but simply the edge of what light has had time to reach us since the Big Bang. Beyond that lies more universe. Not another realm, but more of the same spacetime, receding faster than light can travel, forever beyond our sight. It's not an edge of space, but of visibility. And yet, some theories hint that there may be deeper horizons, not physical walls but informational ones. In the holographic view, the universe might possess an ultimate boundary not in space, but in information. Every region of space can hold only a finite amount of information before collapsing into a black hole. The surface area of that boundary sets the limit. It's not a wall we can touch, it's the cosmic equivalent of the edge of a hard drive. This suggests something profound, that even an infinite universe might be describable by a finite amount of information. That, in some ultimate sense, beyond may not be a place but a concept. Still, the question refuses to die. Philosophers ask, if space is everything, can there be anything outside it? Theologians ask, if the universe has no edge, where is God? Scientists, wary of both metaphors and mysticism, ask a simpler version. What is the universe expanding into? The most honest answer remains, Nothing. But nothing, in physics, is not what most people think. It is not empty. It is the quantum vacuum, a restless sea of energy, particles appearing and vanishing in the blink of a Planck time. It seethes with fluctuations, with potential. Nothing is, in a very real sense, something. And it may be that the universe's expansion is not into emptiness, but into possibility, the unfolding of that quantum potential into the geometry of spacetime. The universe isn't moving through space. Space is emerging from the universe. If that seems abstract, consider a more familiar parallel: time. We don't ask, what is time flowing into? The future doesn't pre-exist as a place waiting to be filled. It comes into being as each moment unfolds. Space may be the same. The universe isn't expanding into pre-existing emptiness. It's creating space as it goes, just as time creates its own future. This is what makes the cosmos so hard to comprehend. It's not a thing in space. It is space. And that means there is no outside, no beyond. Or perhaps there is, but not in the way we imagine. Because if space and time are emergent, if they arise from deeper principles like information or quantum entanglement, then the beyond might not be a physical elsewhere at all. It might be a level beneath or behind the fabric of reality itself. And the hints of that deeper structure are already visible, woven into the equations of both relativity and quantum mechanics. To find them, we must look at the smallest scales, smaller than atoms, smaller than light, smaller than the universe's own fabric. Because the edge that isn't there may not lie at the outermost horizon, but at the tiniest frontier, the quantum heart of spacetime itself. Part 8. The quantum fabric beneath everything we see. Beneath stars and planets, beneath atoms and particles. There is something stranger, subtler, and far less solid than we ever imagined. It is the foundation upon which reality rests, the quantum fabric of spacetime. To the naked eye, the universe seems continuous. Space stretches smoothly, time flows evenly, matter occupies distinct places. But at the smallest possible scales, distances on the order of the Planck length, a mere 10 superscript 3 meters, that illusion dissolves. What we think of as space becomes a seething foam of uncertainty. Physicists call it quantum foam. It's a term coined by John Wheeler in the mid-20th century, the same mind that gave us words like wormhole and black hole. Wheeler imagined that at unimaginably small scales, the geometry of spacetime doesn't behave like a flat surface but like a stormy ocean. Tiny fluctuations in energy twist and fold space itself, creating miniature, transient distortions, micro black holes, wormholes, bubbles of geometry flickering in and out of existence in trillionths of a second. From this roiling chaos, the smooth, stable universe we know somehow emerges. But how? The answer may lie in a principle so counterintuitive that it redefines what we mean by existence. In the quantum world, certainty doesn't exist, only probabilities. A particle isn't in one place or another until we measure it. It occupies all possible positions at once, described by a mathematical entity called a wave function. Even the vacuum, what we call empty space, is filled with these restless possibilities. Physicists once thought of the vacuum as nothingness, but quantum mechanics revealed it as a cauldron of potential, teeming with fleeting particle-antiparticle pairs that spring into being and annihilate each other in the blink of an eye. Einstein once dismissed this as spooky, yet it's real, measurable, testable, and fundamental. When scientists built particle accelerators like CERN's Large Hadron Collider, they found that smashing particles together didn't just break them apart. It pulled new ones from the vacuum itself. Energy turned into matter. The void wasn't empty. It was a field of infinite fertility. So what happens when we apply this quantum logic to space and time themselves? If particles can emerge from the vacuum, then perhaps the vacuum can also give rise to spacetime. This is the frontier where physics blurs into philosophy. Some researchers now believe that spacetime, the very arena in which matter and energy move, isn't fundamental at all. It may be emergent, arising from a deeper layer of reality woven from pure quantum information. According to this idea, the geometry of space is not a backdrop but a byproduct, a pattern created by entanglement. Quantum entanglement is one of nature's most mysterious phenomena. Two particles, once connected, remain linked no matter how far apart they travel. Measure one and you instantly affect the other. Einstein famously derided it as spooky action at a distance. But experiments have proved it again and again. In 2015, physicists confirmed that entangled particles truly behave as a single system, even when separated by kilometers. The connection transcends space. It isn't limited by distance. Now imagine that every bit of the universe is entangled. Not just particles, but fields, energies, and even the vacuum itself. The network of these connections might be spacetime. In this picture, geometry arises from information. The distances between points, the curvature of space, even the flow of time, all emerge from the pattern of quantum correlations. Reality, then, isn't made of matter and energy. It's made of relationships. This radical vision has gained traction in recent years, thanks to new bridges between quantum theory and general relativity. In 2010, theoretical physicists Mark van Ramsdonk and others proposed that spacetime could literally be built from quantum entanglement. Here, the entanglement between regions of the universe apart, and space itself unravels. In simulations, networks of entangled particles form structures that look eerily like curved space, complete with features resembling wormholes. These models suggest that gravity itself could be an emergent property, not a fundamental force, but a side effect of the universe trying to maintain the balance of its information. Einstein's smooth spacetime, once thought of as the ultimate foundation, may only be the visible skin of a deeper informational sea. And here lies the most astonishing idea of all. If spacetime emerges from entanglement, then the expansion of the universe might not be about space growing at all. It could be the growth of entanglement, the spreading of quantum connections across the cosmos. As matter and energy interact, as galaxies form and drift apart, the quantum web linking them becomes ever more intricate. The universe's expansion could be the unfolding of information, the deepening of its quantum structure. In that sense, we are not living in a universe that expands into something else. We are living inside a process of cosmic computation, an expanding web of interconnections, where new regions of space are constantly created as new relationships come into being. We don't move through space. Space moves through us. At this point, the boundary between physics and metaphysics blurs. Are we discovering the mechanics of the cosmos or its code? If the universe is information, then we are part of the message, self-aware fragments of the algorithm observing itself in motion. Every photon that travels, every atom that vibrates, every thought that passes through the human mind contributes to the computation. The cosmos is not expanding into emptiness. It is evolving into understanding. But even as this quantum picture grows more complete, one question remains. If spacetime, matter, and energy all emerge from information, what is information itself made of? To answer that, we must return to the universe's beginning, to the instant when information first appeared, when the void first learned to compute, when the laws of physics themselves were born. Part 9, the first information before light, before matter, before even time itself, there was information. Not the kind we use in language or machines, but the primal logic of existence. The binary distinction between something and nothing, yes and no, this and that. Every physical thing that would ever exist, every atom, every galaxy, every law of physics would ultimately emerge from this simple contrast. In the beginning, there were no stars, no fields, no geometry. There was only potential. And then, somehow, that potential differentiated itself. The universe's first act wasn't creation, it was computation. When scientists look back toward the earliest possible moment, the first trillionth of a second after the Big Bang, the physics we know begins to break down. Temperatures were so high, densities so extreme, that the known forces of nature, gravity, electromagnetism, the strong and weak nuclear forces, were indistinguishable. They merged into a single, unified field, a pure state of symmetry. But perfect symmetry cannot last. Quantum fluctuations, tiny, random disturbances in that uniform field, rippled through the void. The symmetry broke. The unified field fractured into the forces and particles that make up the world today. From that breaking, structure was born. Those quantum ripples were the universe's first information, the first differences that made a difference, to borrow the phrase of cyberneticist Gregory Bateson. Each fluctuation carried a bit of contrast, a deviation from uniformity, and those tiny variations, amplified by cosmic inflation, became the seeds of everything: galaxies, stars, planets, life. In that moment, the universe began to compute itself. Information, in the physics sense, is not abstract. It's measurable, a physical quantity tied to energy and entropy. In 1948, Claude Shannon defined information as the reduction of uncertainty. Every time we distinguish one possibility from another, we gain information. A few decades later, physicist Rolf Landauer extended this concept to the physical world. He proposed that information is physical. It cannot exist without being embodied in matter and energy. Erase one bit of information, and you release a quantifiable amount of heat. Information is not a ghost, Landauer wrote. It is tied to the real world. That means that when the universe began to generate information, when those quantum fluctuations first distinguished one state from another, it was literally converting potential energy into the architecture of reality. Every bit of difference was a spark of structure, a node in the network of becoming. In modern physics, this idea has grown into something profound: the realization that information may not just describe the universe, it may constitute it. John Archibald Wheeler, the visionary who coined black hole and wormhole, proposed that the fundamental building blocks of the cosmos are not particles or waves, but yes-no decisions, what he called it from bit. According to Wheeler, every event in the universe, every photon emission, every particle collision, every quantum choice, is an act of information creation. The universe computes itself into being, one bit at a time. Every particle, every field of force, even the spacetime continuum itself, derives its function, its meaning, its very existence entirely from binary choices. He wrote, "Reality is the output of a cosmic algorithm." If that sounds mystical, it's worth remembering that this digital physics is not about consciousness or simulation. It's about structure. It suggests that the universe's laws are not commands written from above but rules that emerge from consistency itself. Once information exists, it obeys strict principles. It cannot be destroyed, only transformed. Even black holes, which seem to devour everything, must preserve the information that falls into them, encoded, perhaps, on their event horizons. This principle, tested and debated for decades, now underpins one of the most astonishing ideas in physics: that the universe, as a whole, behaves like a quantum computer that never loses a bit of its own history. Every interaction, every particle decay, every photon that ever traveled through space, all of it is still there, written into the fabric of reality. The cosmos remembers everything, and what we perceive as time may simply be the process of that information updating itself, the universe computing its own next state. From this view, the Big Bang wasn't a detonation in space. It was the moment when information began to propagate, when the first distinction gave rise to the first relation, and the first relation gave rise to space, time, and causality itself. If the universe is a computation, its expansion is not a spreading of matter through void, but a blossoming of data, a recursive unfolding of possibility into form. Each new moment isn't another frame in an endless film. It's a new layer of calculation, a fresh iteration of the universal code. And the code is elegant beyond measure. A self-updating system where energy and entropy, order and chaos, geometry and information, all evolve together. This brings us to an even deeper question: why? Why should there be information at all? Why should the void compute? Some physicists, like Wheeler, saw this as inevitable, a natural consequence of quantum mechanics. Others, like David Deutsch, argue that computation is the most general description of reality possible. Everything else, from physics to thought, is a special case of information processing. But there's another possibility, one whispered by philosophers since the dawn of inquiry: that the universe generates information because it is self-aware. that consciousness, in some form, is not an emergent property of matter, but a fundamental aspect of the informational process itself. If true, then perhaps the cosmos isn't merely computing its next move, it's knowing itself, learning through its own unfolding. We, as thinking beings, might be that process made self-reflective, the universe, in the words of Carl Sagan, becoming aware of itself. And if information is eternal, then awareness, however fleeting in its local forms, might be eternal too. Because to know is to distinguish, to create difference, to generate information. And that, it seems, is the one thing the universe has been doing since the beginning. So perhaps the first information wasn't a command or a number, but a question. A single, self-referential question that broke the perfect symmetry of nothingness. What am I? And everything that has happened since, every atom, every galaxy, every thought, is the universe's attempt to answer it. Part 10. The universe that knows itself. There is a moment, fleeting, immeasurable, when a newborn opens its eyes for the first time. Light, shadow, form, and movement flood into awareness. The world begins not as objects, but as relations. Brightness against darkness, warmth against cold, sound against silence. In that instant, the mind awakens by distinguishing. In a way, the universe did the same. When it first opened its eyes, when symmetry broke and information began to flow, the cosmos became capable, in the most primitive sense, of perceiving itself. From that moment onward, reality was not a static thing but a dialogue. Between order and chaos, energy and entropy, matter and void. That dialogue has never stopped. And somewhere along the way, it began to speak through us. We are not separate from the universe's unfolding. We are its continuation. Every neuron that fires, every thought that arises, is built from atoms forged in the hearts of long-dead stars. Our brains are miniature galaxies of matter and information, running on the same physical laws that govern the cosmos itself. When we look at the sky and ask what is it expanding into, the question is recursive, the universe asking itself about its own nature. The poet Rainer Maria Rilke once wrote, "The universe is not outside of you. Look inside yourself. Everything that you want, you already are." Physics, in its own austere language, is beginning to agree. In the quantum view, information is not passive, it's active, dynamic, self-organizing. Every system that gathers and processes information, from a star to a cell, increases the universe's internal complexity. Life, and especially consciousness, may not be an accident of this process but its inevitable expression. The biologist Lynn Margulis once said that life is the way the Earth keeps its surface chemistry out of equilibrium. In informational terms, consciousness may be the way the universe keeps its meaning out of equilibrium, a perpetual self-measurement that prevents entropy from having the final word. We think we are observing the universe. In truth, the universe is observing through us. This idea isn't mystical, it's mathematical. In quantum mechanics, an observation isn't just a human act. It's any interaction that collapses possibilities into a single outcome. When a particle's position is measured, what really happens is that its wave of probabilities becomes entangled with another system. Information is exchanged, and uncertainty reduces. In this sense, the entire universe is engaged in an endless act of observation. Every atom interacts with every other, every photon with every field. The cosmos measures itself continually, updating its information state moment by moment. Consciousness, then, could be the localized, recursive form of that universal process, information reflecting upon itself. The physicist and philosopher David Bohm once suggested that what we perceive as separate things are actually projections from a deeper, unified order he called the implicate order. In this framework, everything is enfolded within everything else, just as every point in a hologram contains the whole image. Consciousness, in Bohm's view, was the universe's way of unfolding itself, bringing hidden patterns into manifestation. He wrote, "The observer and the observed are one. The universe looks at itself through our eyes." Modern physics echoes that sentiment in surprising ways. In the equations of quantum information theory, the boundary between observer and system blurs. What we call reality may simply be the shared information created at that boundary, an ongoing conversation between the cosmos and itself. From this vantage point, the universe is not a cold, indifferent expanse of matter. It is a living network of meaning. Every photon that leaves a star, every neuron that fires in a brain, every question whispered into the void adds another layer to the grand computation. The cosmos is not expanding in space, it is expanding in awareness. Each new galaxy that forms, each new mind that arises, extends the reach of that awareness a little farther. We are not at the center of the universe, but we are central to its story, not as masters, but as witnesses, participants, and expressions of its unfolding intelligence. The physicist Freeman Dyson once said, "The universe knew we were coming." Perhaps he meant it metaphorically, or perhaps he intuited what information theory now implies, that consciousness and cosmos are not two separate things, but two faces of the same self-organizing principle. In that light, every act of knowing, every discovery, every insight, every quiet moment of wonder, is a form of cosmic self-recognition. When we map a galaxy, decipher a genome, or fall in love with the night sky, we are not reaching outward into the unknown. We are turning inward, toward the infinite reflection of what we already are. And so we arrive where we began, two trains on parallel tracks, converging where they should never meet. The lines of matter and mind, of physics and perception, of geometry and meaning, once thought to be forever separate, meet at last in the same place, within us. For the universe that began in darkness now looks back at itself through eyes of light. And as it does, one truth becomes clear. The universe is not expanding into emptiness. It is expanding into understanding. Epilogue: the night of geometry there is a silence older than stars. It exists in the spaces between numbers, in the pause before a thought becomes a word, in the infinitesimal interval between nothing and something. It is the silence of geometry before it learned to draw, the stillness of reality before it learned to move. For thousands of years, humanity has tried to describe that silence. We have done it with circles and theorems, with prayers and telescopes, with equations so dense they look like spells. Every time we push further, every time we think we've reached the edge, the silence deepens. Euclid called it perfection. Grosseteste called it light. Einstein called it spacetime. We call it the universe. But perhaps they were all speaking about the same thing, the geometry of the unknown. Once, the world was flat, not in its shape but in its certainty. Parallel lines never met. Angles behaved. The universe was measurable, contained, and, most comforting of all, comprehensible. Then came the heretics of geometry, Bolyai, Lobachevsky, Gauss, Riemann, men who dared to ask whether space itself could lie. Whether the truths we called eternal were only local customs of a larger, stranger cosmos. Their rebellion against Euclid's fifth postulate tore a hole in the fabric of reason, a tear through which light and later Einstein would pour. Because when geometry became flexible, reality did too. Now we know that space bends, that time dilates, that gravity is not a force but a curvature, that energy and information are the same. And yet, in learning this, we have returned, almost unwittingly, to the mysticism of our ancestors. For what is a curved spacetime but a divine loop? What is entanglement but the whisper of unity? What is the holographic principle but the echo of as above, so below? Science has not dispelled mystery. It has refined it. The farther we peer into the equations, the more they resemble poetry. Today, we can describe the cosmos with exquisite precision. We know its age, 13.8 billion years. We can measure its temperature, map its background radiation, trace its chemical evolution from hydrogen to humanity. But precision is not the same as understanding. For all our instruments and mathematics, we still stand before the same paradox that haunted Grosseteste's candlelit chamber and Lemaitre's prayerful chalkboard. If the universe is expanding, what is it expanding into? The physicist says, nothing. The philosopher asks, how can nothing expand? The poet whispers, into itself. And perhaps that is the answer. Because in every age, when we reach the limits of our knowledge, we meet a mirror. The more deeply we look into the cosmos, the more unmistakably we see our own reflection staring back. We once thought geometry was about space. We have learned it is about relation. We once thought physics was about matter. We have learned it is about information. We once thought consciousness was about life. We are learning it may be about the universe itself. Each revelation collapses another boundary. Each breakthrough is a soft collision of parallels. At the end of his life, Gauss was asked whether he believed in God. He hesitated, then answered, "That depends on what you mean by God." Perhaps what he meant, what all seekers mean, is the invisible symmetry between knowing and being. The recognition that the laws of physics are not just descriptions of the universe, but expressions of its self-awareness. In that sense, geometry is not the study of space. It is the language of creation. And so the night of geometry is not darkness, but potential, the womb of all form, the silence that gives shape to sound, the void that allows light to be born. When Robert Grosseteste wrote of lux, the first light radiating from a single point, he was not describing physics as we know it. He was describing something deeper, the moment when reality decided to exist. That moment never ended, continues still. Every second of our lives, every expansion of space, every act of perception is another flicker of that original light. We are living within the first instant of creation, stretched across billions of years, unfolding toward comprehension. So, at the end of this long inquiry, through Euclid's postulates and Einstein's equations, through brains and holograms, through particles and paradox, we arrive where we began, standing in the dark, trying to understand light. The universe expands, not into emptiness, but into awareness. Its edges are not boundaries, but horizons of understanding. And the geometry that defines it is not merely spatial, but spiritual, the shape of knowledge as it turns back upon itself. Somewhere, in the infinite silence, a question still echoes. The same question that shattered the void at the beginning of time. What am I? And the universe, forever expanding, forever learning, forever reflecting, answers in galaxies, in mathematics, in minds. I am this.